In this video, we'll go over MATLAB's functions for solving ordinary differential equations. After studying this video, you should be able to explain the concept of adaptive time stepping, use MATLAB's built-in ODE solvers for the solution of ODEs, understand the basic concepts of the algorithms that are at the heart of most of MATLAB's ODE solvers, and study the truncation error behavior of an adaptive method. So first let's talk about adaptive methods, which is the case for most of MATLAB solvers. So we got to understand what is this idea of an adaptive method. So this gets at the thing we talked about before in the context of stiffness, is that many solutions exhibit multiple timescales. And remember what we said before is if those timescales are widely varying, that's where we get to that idea of a stiff ODE. But in general, a lot of solutions exhibit multiple timescales, and here's an example here where we have a slowly changing function and then a rapid change in the derivative here and there, and then back to a slow change. So here's a short scale and then a longer time scale. Adaptive ODE solvers actually will change the step size as the integration progresses depending on the behavior of the solution. So it has some way to test the behavior of the solution, and then actually will reduce the step size if necessary to maintain accuracy through those quickly changing parts of the solution. And this is just some example solution over here to the right. So let's look at how this works. So there's two basic approaches to adaptive methods. The general idea is to solve each time step in the solution at two levels of accuracy and then compare the results. So we'd have a more accurate solution and a less accurate solution, and we could look at the difference between the two and compare them to some stopping criterion or tolerance. If the more accurate solution is not that much better than the less accurate solution, in other words, we're within the stopping criterion, then we would move to the next step. If it is a lot better, or we haven't satisfied our stopping criterion, then what we would do is cut the step in half and recalculate half a time step. So there's two approaches to checking the accuracy of the solution this way. One is called step halving, and the way we do that is we'll just calculate that less accurate time step by calculating yi plus 1 using a full time step, and then calculate the more accurate approach by calculating yi plus 1 using 2 half steps. The other approach is to use an embedded Runge-Kutta method. Recall that Runge-Kutta methods are one-step methods, and the difference between the methods is how we calculate that increment function phi. So a way that we can do that is to calculate our less accurate using a second-order method. For example, here's a second-order method, Runge-Kutta method, and then calculate our more accurate result using a third order method. And this approach can actually be very efficient because what we can do is we can set up a Runge-Kutta method such that the third order method uses the same first two terms. So the A1 and K1, those first constants and function evaluations, are the same as for the second order method. So our higher order method, remember we have some flexibility in how we formulate a Runge-Kutta method because we choose one of the constants, and it can be done to formulate that higher order method as one additional term to the lower order. And this makes the embedded Runge-Kutta methods are preferred for adaptive time stepping because they are more efficient. Here are a few of MATLAB's general use ODE solvers. ODE 2.3 is a second and third order embedded Runge-Kutta solver, and remember that embedded Runge-Kutta is how the adaptive time step is implemented. ODE 4.5 is a fourth and fifth order embedded Runge-Kutta method. This solver is recommended by MATLAB as the first solver to try, meaning it's probably going to work most of the time for most ODEs. And when I say work, that means a stable and accurate solution. But sometimes it won't work and we need to use another method. One of those methods that can be helpful when ODE 45 doesn't provide an accurate solution is ODE 113, and that's a variable order Adams-Bashforth-Moulton method. Recall that's a predictor corrector method, so it's a little more stable since it's a predictor corrector than ODE 45. And it's variable order, meaning it uses different order calculations of Adams-Bashforth-Moulton to adjust the time step. The syntax for MATLAB's ODE solvers is similar to what we've been using for setting up our own function M files that we've been writing for ODEs. We have outputs T and Y, where Y is a matrix of the solutions for the different components of the system of ODEs. They're all set up for a system of ODEs. So the Y solutions, again, are in a matrix, Y1, Y2, Y3, etc. dy dt, that's a column, that is a function that returns a column vector of the f sub I of the ti yi's, or f sub j, call it, of the ti yi's. T-span, now here's something that's a little bit different. So the time span, there's actually two options for how you send that to MATLAB's ODE solvers. One option is if you just have the initial time and the final time, then the T output from ODE 45 is the actual time steps from the adaptive algorithm. If you send it an increment, so like T naught and then some delta T increment, so a vector of time values up to some final time value, the function itself is still going to use the adaptive algorithm to do the integration, but it's only going to report out the T output and the corresponding Y outputs. It's only going to report out the steps specified in T-span. So a little different there. So if you only want to know the solution of the equation in, say, 0.1 increments, then that's where you can specify that by sending a delta t, or a vector of time values, to T-span. Similar to what we had before, we have y naught is our row vector of initial conditions. Options we're going to talk about on the next slide. This is how we set some options for the solver. And then we can pass parameters through the solver for our dy dt function to use to evaluate. So let's talk a little bit more about those ODE solver options. So the way we specify options for the ODE solver is similar to the optim set command, and recall we were using that for F0 and fmin search earlier in the quarter, but it's a different command called ODE set. So this is the set of options for the ODEs, and similar syntax where we specify which parameter are we setting and then give it a value. So some commonly used parameters are reltol, that adjusts the relative tolerance for the adaptive time stepping, and abstol adjusts the absolute tolerance for the adaptive time stepping. So both of these are for that time stepping. And the way that it works, again, thinking about that adaptive time stepping, we look at yi plus 1 using the more accurate approach, generally with an embedded Runge-Kutta method for, say, ODE 45 or ODE 23, minus yi plus 1 for the less accurate approach. And then since we have two tolerances here, a relative tolerance and an absolute tolerance, it's going to actually check both of those tolerances and make sure that our time step is within the tolerance, both the absolute tolerance and then the relative tolerance times the magnitude of yi plus 1, and that would be the more accurate value of yi plus 1. So what we're doing here is just checking both the absolute tolerance and the relative tolerance before moving on to the next time step or cutting the time step in half. Some other options that are commonly used are the initial time step, and you can use the initial time step to start with a smaller step size perhaps. If you know that it's going to get to a small step size, this can be a little bit more efficient to start with a small delta t if you know you're going to end up there anyways, or the maximum step size, which is a default to 1/10 of t-span, of the interval in t-span, if you give t-span an interval. The maximum step size will keep delta t from being too large. So you make sure the output is basically has enough points for a smooth plot, is one way to think of about that. So let's look at an example solution using ODE 2.3, which illustrates the adaptive time stepping. So here's two solutions on that previous differential equation that I used to talk about the idea of adaptive time stepping. And I'm not really worrying about the equation itself. I just want to show conceptually what's happening here. And here's with a relative tolerance set to 1 times 10 to the minus 3. The circles are the values from ODE 2.3, and you can see that as we get to these faster changing regions, we get a smaller h, or a smaller time step. Increasing the tolerance, decreasing the tolerance to a tighter value of 1 times 10 to the minus 4, we see a lot smaller, significantly smaller h value through that quickly changing region of the solution. But we also see that there's pretty much the same, h is the same in the slower changing region. So this illustrates how that adaptive time stepping gets us more computational efficiency. In other words, we're only using the small h where we need to, like in this region, use that small h only where necessary for our desired accuracy. MATLAB also has some ODE functions designed specifically for stiff systems. Those two functions are ODE15S, that's a variable order solver based on numerical differentiation formulas. It's using a gear method, which we actually haven't talked about in this class. it's basically an application of those finite difference formulas, and it's an implicit method, which is useful for stiff systems. And ODE 23S is based on a modified second-order Rosenbrock formula, which is very similar to an implicit second-order Runge-Kutta. And this might be more efficient for crude tolerances. So how to choose which solver, the syntax of these are the same. One thing we run into is like MATLAB has all of these different solvers. How do we choose which one to use? And again, the first choice is generally going to be ODE 45. So that's our first choice. So we try ODE 45 and we see what we get. If ODE 45 seems like it gives us a good solution, then we might be fine with it. We might also go to a lower order solver like ODE 23 and see if we also get a good solution with that, because it might be, since it's a lower order solver, it would take less time to compute the solution. If ODE 45 doesn't work, it might be that we have a stiff system, so we could run some numerical experiments to see if the system is stiff, and maybe go to one of the stiff solvers like ODE 23S. So to see an example of that, let's look at this example using the van der Pol equation, and we'll solve for y in the van der Pol equation for the following two cases. For the first case, with mu equal to 1, we'll solve for t from 0 to 20. And for the second case, with the parameter mu here equal to 1,000, we'll solve for t from 0 to 6,000. And what we'll see is that for mu equals 1, this is a nonlinear differential equation that we can solve using pretty much any method. For mu equals 1,000, this actually becomes a stiff. When we write this as a system of two ODEs, this is a stiff ODE for mu equal 1,000. So let's look at some MATLAB code to solve this. So here's our MATLAB code, and we'll solve it for the first case with mu equal to 1 passed as a parameter there, using default tolerances and default options. So just putting the placeholder there to get to the parameters. Solving with ODE 45, and then we'll plot that. And then I've commented out the ODE 45 solution, and I would encourage you to try running this M file and see what happens with the ODE 45 solution, because actually what you'll find is the ODE 45 solution, it never converges. It reaches its limit on the adaptive time stepping and basically fails. And that's because of the stiffness of the system, or of the ODE. But then we can try solving with a solver that's actually built for a stiff system, ODE 23S, and we find that that works. And we can look at a plot of the solution and really see that stiffness. So here is a plot of y and dy dt for mu equals 1, and we see kind of a smooth oscillating function moving through. When mu goes to 1,000, we see this really abrupt periodic change, and that is an indication of the stiffness in the system that we can also see in the plot of the derivative. That spike in the derivative is another indication of stiffness in the system. The last thing I want to talk about is the accuracy of the adaptive solvers, or as we've talked a lot before, the behavior of the truncation error, ET. One way to determine the order of accuracy of MATLAB solvers is to run a numerical experiment. So recall, we usually think of the local truncation error behavior as being some ET, solvers being some order h to the n, where n is the order of a solver. So what we're saying is that truncation error is proportional to h to the n. So another way to think about that is we're saying ET is equal to some constant, some unknown constant, times h to the n. Well, if we take the log of both sides, we take the log of ET, that's going to be equal to the log of C plus n times the log of h. And what we can do is those tolerances absolute tol and the relative tolerance on these adaptive solvers, these basically are setting what that local truncation error needs to be in order for the integration to progress. So they actually give us a measure of the local truncation error, and what we can do is plot the log of ET versus the log of h, and n will be the slope of that plot. So let's look at what that looks like for two of these solvers. And this is actually in solving the van der Pol equation again. And it'll change a little bit depending on which differential equation you're solving, how stiff it is, what type of oscillations the solution exhibits, etc. But what we see here is plotting the error tolerance, and what I've done is done this on a log-log plot. So we're looking at logarithmic scales here. And we see the slope here in dashed black lines, the slope of the ODE 2,3 solution. Again, this is with the mu equals 1, so it's not a stiff van der Pol equation. With ODE 2,3, we get a slope of 3.2, and with ODE 4,5, we get a slope of 6.2. So, and these are local errors, so we would conclude from that slope that that solver acts globally as about order h squared, and that's global error behavior. And for ODE 4,5, we would conclude that that solver acts, we'd subtract 1 off that, and it's all approximate, so we'd make it an integer, so we'd say it's roughly 5th order accurate in terms of a global error. And so we can run an experiment like this on any differential equation to get a sense of how the accuracy will improve as that time step is reduced for that specific solver.